Hello, Assalamu alaikum, students. This is Synchronous Generator lecture number 2, and today we will be covering from article 4.6, 4.7 and 4.8 of chapter number 4. I hope you have gone through Synchronous Generator lecture number 1, where we actually talked about the synchronous generator equivalent circuit. We talked about this phasor diagram. We talked about different types of synchronous generator. Then we also talked about the brushless exciter and the pilot exciter. Today we are going to go a little bit more into the equation stuff, dealing with the phasor diagrams again. We will find out the derivation for the power equation of a synchronous generator, and then we will move on towards a simple test that can be done on a synchronous generator, and then the last one, that is about the synchronous generator when it is working, what happens when you increase the load or decrease the load on that generator. So first of all, just a little glimpse from the first lecture. As you can see over here, what I have done over here, I have the three phasor diagrams already taken from the book, which are for the inductive load, as you can see, and then the capacitive load and the resistive load. The reason I have actually made them over here from the book is this, that I want to actually show you that the vectors IARA and the vector JXSIA, these two vectors are very small over there. Now practically, if you remember your lecture number 1, I drew them a little large, and in fact in this book, even in fact this image also, it has been made a little bit large so that it's actually visible. But practically the resistance of the windings, which is RA, which is per phase resistance, that is very small. So this IARA vector is technically very small, and JXSIA vector also is very small, because XS may be a little larger than RA, but a little again a very smaller length as compared to the other big vectors, which are V phase and EA. Now for those who are still a little bit lagging behind, that what I'm actually talking about here, these are the three phasor diagrams over here, which has been drawn for this equation, where EA, now I'm not going to draw the phasor the vector symbol over every time, because now this is clear to you that these are all vectors or phasors over here. So V phase plus IARA, and then I have JIAXS. So all these three phasor diagrams which you are seeing over here, they have been drawn for the inductive load, capacitive load. Sorry about it, I guess this has been made a little wrong over here from my side. This is it has been written opposite over here. This is actually in fact capacitive load, because as you can see, this is current is leading, and if you see this one, this is inductive load over here, as the current is lagging over here, and then over here the IA current is in phase with the phase voltage, so that's why this is called as a resistor. Sorry about this mistake, actually I copied them from the book and then the sequence was actually disturbed, so that's why. Okay, now this was just a repeat from the last lecture, if you remember over here. Now all these three phasor diagrams over here, they are including this vector IARA, JIAXS, and then certainly V phase, and in the end we find out this EA. Practically, when we have any generator in front of us, since we know this RA, that is actually the resistance of the winding, this is approximately very small value. So what happens to this equation over here? That was this equation we just talked about. This equation over here, which is actually the generator equation over here, this reduces to, if I'm assuming that RA is very small, so this EA is just equal to V phase plus JIAXS. Now please, this is an approximate equation, not the actual equation. Why we have done this? Because this RA resistance, which is actually the resistance of the per phase of the synchronous generator stator windings, or actually the armature windings, it's very small, maybe in something in micro ohms or milliohms, or not in fact in ohms. It can never be in ohms or something, because a generator is actually going to provide this So this means actually that you are actually going to have a resistance very small. So you reduce down the copper losses. You have to make this very small. Now the reason of actually doing this one, because if you are going to have this EA is equal to V phase plus JIA XS, which is equal to this phasor. Now normally the load which you are always having is resistive load, generally speaking, or an inductive load majorly. So now I'm going to redraw this phasor diagram just for the inductive load. So today I'm going to try to make this phasor diagrams a little bit more clean over here, so that actually you can copy this one very easily. So this is my V phase over here, and then I will use another color over here for my IA, and this is my IA over here. And now over here, since I have not to add now over here IARA, so what I will do over here, if you can just see over here, this is a little technique over here which is used in your book also. What you can do over here, just extend this a little with a dotted line and try to make a right triangle. Now this angle is 90 degrees, so certainly this means that if I'm now going to add, let's just me add with another color over here. So I have this one as J I. Let me just this is my J I A axis. So this means now when I'm going to complete this vector, let me just use another color over here. In fact, we use a dark color over here, so it's easy for. This is my EA. And certainly, as we have talked before, this is the delta angle over here. Now if you're seeing this phasor diagram, this has ignored IARA. So what happens now? Without going into the proof of it and all that, I'm just going to use this phasor diagram now. So what I'm going to do over here, let me just take another color over here. So if I extend this over here, and I draw a perpendicular vector over here. So what I have now, this is a perpendicular. Now if you are seeing this phasor diagram over here, if this angle was theta, which means that current IA was actually lagging by an angle theta behind V phase, this angle is 90, so this means that certainly this angle is also going to be 180 minus 90 minus theta, so this angle would be something 90 minus theta degrees. And certainly since these are alternate angles over here, just two bisectors, so this is also 90 minus theta over here. And since this is 90 degrees, since I have just drawn a perpendicular over here, this angle is equal to theta. I hope this is clear. I'm just repeating it again. If this is the angle IA that is having the V phase, that is angle theta being over here, that is the lagging angle. I have reproduced this triangle over here, extended to the dotted line, and then I have put this J axis, and then I have completed this two right angle triangles over here. These are two opposite angles. So this angle is 90 minus theta. This is also 90 minus theta, because completing the whole triangle, this is 180 degrees. So this is 90 minus theta, this is 90. So certainly this means that this has to be 90, so that the whole sum is actually equal to 180 degrees. Now if you are seeing over here, this factor which I am indicating over here, this is going to be, since this is the vector IAXS over here, and this is that angle theta, so this length over here is actually equal to, if I'm correct with the trigonometric, so this is equal to IAXS cos of theta. Why? Because this is the x component. If I have taken this length over here, this would be equal to IAXS sine of theta. Now over here, this length, the same length over here, if I use the other color over here just for the difference, let me use another color over here. So if I have this one, the same vector length, so can I also call this length equal to EA sine of delta? Because this is that vector EA, so this is the y component over here for this delta angle. So this means that these two are the same thing, just values different over here. So what this means over here, that if I now going to write down this equation over here, that using the color, the dark color over here. So this is IA XS cos of theta equal to EA sine of delta. Now this is a very interesting equation over here. I'm just going to rearrange this a little in form. So this is IA cos of theta equal to EA sine of delta divided by XS. Now this is going to be used in our equation. Now this is actually very simply, this is telling you that actually the x component of the current over here, IA cos of theta, is equal to this expression, which is EA sine of delta divided by XS over here. Now whenever you have a generator in front, let's just see this equation over here. Whenever you have a generator in front of you, and if you just go to your previous lecture, or if you open your book, we have found out if generator is connected in Y configuration and you want to find out the total output power of that generator. This is very important. If you want to find out the total output power of your generator and it is Y connected, this is again Y connected over here, so that will be equal to under root 3 times VL, that is line voltage. We already know this formula from our CAD course. So this is the IL cos of theta. I hope everyone has this idea. Now since we don't know VL, we know VL is actually line to line voltage is equal to under root 3 times the phase voltage. Sorry about it. So this will be equal to 3 V phase, and what is IL? IL is the same as IA. So this is equal to cos of theta. So the output power is actually equal to 3 V phase, or actually V phi over here, because this is a phase voltage, and the line current or the phase current, they both are the same. So this is 3 V phase IA cos of theta. Now if you see in this expression over here, this term over here, that is IA cos of theta, can be replaced from over here, this expression. Now what happens over here, this P out, that is actually the output power, that changes to 3 V phase. If I put this value over here of EA sine delta divided by XS. Now this is a totally different new expression, and it does not take any angle or any current value. Now in this equation, if you notice over here, XS, it's a constant of a machine that is supplied by the manufacturer. 3 numerical constant, V phase, EA. Now if a generator is working alone, means supposedly if you are sitting in a room and that generator is actually just being provided that room over there, then maybe V phase and EA, they will be changing, because maybe there is a turbine over there, the speed changes or whatever, then EA is also going to change. But technically this V phase and EA, if you can measure this too, and you know the angle, that is actually called as the torque angle. Why it is called a torque angle, we just see that a little later now. So this is the P out formula over. Now this P out formula, let's just call it as equation number A. We will come back to it a little later just now. Now the power that was actually applied to this generator, now if we go back on this one and we see the power applied to this generator, so the power converted, that was actually the power converted from the mechanical into the electrical. So that was equal to, if I talk in terms of the torque, that was the induced torque into omega m. You all know this formula, is P is equal to tau omega. Now this P converted, because when it is converted, it is actually, if I draw the equivalent circuit over here again, because this is required over here, this is the equivalent circuit. I'm only drawing the stator side over here. This is the resistance, this is the XS, and then this is that EA source, this is that RA source, this is that JXS, and certainly this will be the V phase over here. So if you see over here, the internally generated voltage is EA, and then I have the angle over here that the current goes on, and then it is connected to some load over here, and that load can be single phase or 3 phase. So over here the converted power is actually the power which is at this point. So this means that your P converted electrically, that will be equal to EA IA into cos of the angle between EA and IA, and that we are going to call it gamma. Now what is this gamma over here? Since if I go back on my equation over here, or the phasor diagram, EA and V phase, they have an angle delta. V phase and IA, they have an angle theta over there. So this angle over here, this one, this is called as the gamma. I hope this is clear, because this is the internally generated voltage, and then afterwards passing through that resistance and that reactance, which is actually because of the armature reaction and a self-inductance, it reduces to V phase. So the P converted, that is actually the electrical power which is converted, is equal to EAIA cos of gamma. So this is the converted power, and this is the output power available over here in the form of equation 3V phase EA sine of delta divided by XS. Now similar equation, if I want to write down for the reactive power, let's suppose if I have a reactive power, and reactive power, we know that reactive power Q out, we know the general equation is equal to under root 3 VL IL, and here this time this is sine of theta. So this time if I want to write down this reactive power, which is actually Q, this will be 3V phase IA sine of theta. Now here there is no expression, you cannot substitute anything for this IA sine of theta. Why? The reason, maybe you can come out with some expression over there, but it's not needed. Now the answer to this one is a little bit tricky over here. Generators, whenever they are actually run, they are always run for their electrical power, that is actually active power. Reactive power is never required from a generator, supposedly a generator at Tarbela Dam or Mangla Dam or maybe anywhere else. So it is never required over there. We always require the active power. The reactive power is generated by capacitors near your grid stations, so that you can actually, they don't need to go towards Tarbela Dam or Mangla Dam or near your powerhouses. They can just flow, because reactive power, we know it flows from the source towards the load. So this means actually that you are going to have that power just flowing from your home or your device, which is inductive load, towards your grid station where the capacitors are attached. If it had to flow towards Tarbela and Mangla or maybe any other powerhouse, maybe 1000 or 2000 kilometers away, then it is going to be an extraordinary current flowing through the transmission lines. And we know if more current is flowing through the transmission lines, this actually means that you are going to have more I²R losses, and certainly more heating, more line losses also. The term line losses normally usually used in the power industry basically, or the generation industry, actually accounts for all the losses which are happening in the transmission lines. Maybe some theft is also included inside it, but that happens actually at your load centers, or actually the points where the power is actually being consumed. Okay, so I hope this is clear over here. So this power out formula over here is equal to 3 V phase EA sine of delta divided by XS over here. Now this expression over here, as you can see in this expression is going to have a maximum value based on sine of delta. Now this delta angle, theoretically we know this is going to be, if it goes to 90, then sine of 90 is equal to 1. So this means that if I again write down this expression of this P out is equal to 3 V phase EA sine of delta divided by XS. So over here, if I want to write down P max, what is P max over here? P max will be equal to 3 V phase EA divided by XS. Here sine of delta, over here I have taken that sine of delta equal to 1, and I have taken this delta angle equal to 90. Now here is the interesting point over here. Whenever this delta angle becomes 90, if I go back on my phasor diagram, if you see this one, can angle delta, which is actually the angle between EA and V phase, become 90 degrees? No, there is no way possible that you can actually have a 90-degree angle. Why? Because you cannot have two vectors at 90 degrees to each other and they are completing an actual triangle over here, which is actually the triangle of IA XS and IARA, if it is included over there. So practically there is no way that you can have actually this delta angle equal to 90. So this limit over here, or this expression, is just a theoretical value, the practical value of delta angle, which we normally use it, we are having an angle of 20 degrees to 30 degrees, which is the practical working angle of delta. So a maximum generator can actually produce is an angle 30 degrees over there. That is actually the delta angle between EA and the phase over there. So this delta angle is just limited to this value. Now, why this is limited to this value, why it is not 45 and all that stuff, it actually goes in the design of the electric machine or the design of the synchronous generator. So I'm not going to go in much detail over here. But if I have this expression again over here, and here in this expression, if you want to find out the total torque over here, so if the torque that is actually being applied over there, so just we know that torque is equal to power divided by omega. So this expression can be equal to 3V phase EA sine of delta divided by XS, and here you have that omega m also. So this means that if this is the torque applied from a mechanical source towards this generator, you are going to get something as an output over there. So the power output that requires this T or the torque actually exerted from that mechanical source over here. Okay, now concluding this one or this thing over here, if you are seeing this one, let's just see towards the power flow diagram that we have already seen in different motors and all that stuff. Let me just okay, now what you can see over here is the power flow diagram of the synchronous generator over here. This is the input power, which is actually torque applied into omega m. Omega m is actually the speed over there. Then there are some stray losses, as you already know, whether those losses can be because of the aging of the bearing or the aging of the winding, or maybe any other intermittent error that is available over there. Then there are friction and windage losses because the rotor is moving at a very high speed. There are bearings, there is an air friction always present over there, and then certainly, as we all know, it's a machine, so it's always going to have core losses over there. And one thing very important over here, still you are applying DC current to your rotor. But this is very important that the rotor is also laminated. This is very important. The reason behind it is you are applying a DC, but it is rotating. So when it is rotating and it is interacting with the stator flux, there is a rate of change of flux involved. So there are going to be eddy current losses. Please remember, eddy current losses are always produced whenever there is a change in the flux over there, and they try to flow perpendicular to actually the direction of the flux. So if the flux is flowing towards the stator, then they will try to flow towards the axial nature of your rotor over there. So core losses are always there, and they are present in the stator as well and the rotor as well. There is no exception over here. Just like the induction machine, if you remember, in induction machine the rotor was not having enough core losses, or we can call it the eddy current losses was not there, because the frequency of the induced EMF inside it was very small, and that was just like 1 to 5% of the 50 hertz applied if you are working the motor in Pakistan. Okay, so after this point we have the converted power. We just wrote this equation over there as well, that this is the converted power at this dotted line point. And then afterwards, after passing through the iron losses, or sorry, the I square R losses, which are the copper losses, you have the output power, and this is the same output power. We have just called it as 3V phase EA sine of delta divided by XS over here. So I hope this is the power flow diagram of a synchronous generator, and I hope this is clear. Okay, now when we have got the power equation, we know what synchronous generator requires the power, we know the delta angle limits as well. But before we proceed on further to how a synchronous generator behaves, or how a synchronous generator actually deals with loads and the loads are changing, we need to find out these three parameters. We already know very well. We know RA and we know XS. These are the two parameters of any synchronous generator. So we need to find out RA and XS. So how to find out these ones? Very simply one, for RA it's very simple over there. If the winding of any synchronous generator is going to be connected in supposedly Y configuration, you need to find out the resistance of the windings. Very easy way, you have to, this is the stator winding, remember this is the stator winding resistance that I want to find out. You just have to apply a small DC voltage, and that DC voltage will apply a DC current flowing over here. I am assuming that DC conventional current is flowing. So over here, that current is going to flow through this resistance. This is that RA, this is that RA, and since this is Y connected, my RA will be equal to this VDC divided by 2IDC. Now one problem with you over here is this: since you are only applying the DC voltage over here, the current is actually going to flow through the resistance, but this value of resistance will be actually the DC resistance. It will not have the property of the AC values over here. The reason over here is this, that in AC there is a skin effect, and skin effect always comes into play whenever there are high frequencies involved over there. So technically speaking, this RA, you will have to change it from a DC value to an AC value, but maybe at this level, at undergraduate level, you can still use the DC value. So this value of resistance which you are going to get is going to be a DC resistance over here. Now this is completely simple, and I hope this has been done in the induction motor as well, so you already are familiar over here. Now for excess, which is actually a tricky thing because it actually has the inductance as well, that is actually the self inductance, and it also has the armature reaction. Now the test which is going to be done over here, again that test is summarized over here into two categories. One is called as the open circuit test, just like the transformer or the induction motor, if you remember it, and the other one is called as the short circuit test over there. Now first of all, talking about the open circuit test, that is OCT over here, and if you can see over here what we have done, this has on the left of my screen over here, what I have a curve over here in which on the x-axis I have my field current, and on the y-axis I have my voltage. Now this voltage over here is the very same as EA or VT. Now since this is open circuit characteristics, so this means that I am not going to attach any load. I'm going to run the generator at its rated speed. One thing very important over here, the speed is a very critical factor. Just like your magnetization curve experiment which you have done in the lab, your EA has to be kept, EA is equal to K phi omega. So over here you are changing flux phi by this IF current. So over here you have to actually keep the omega speed constant, and the other condition of keeping that omega constant is also this, that if you will keep omega constant, the frequency of the EMF that is available to you out the armature winding or the stator winding, that is going to remain constant. So this curve has been plotted with omega constant over there. Let me just write it down. So this curve has been plotted with omega constant over here. Now as you can see over here, there are actually two curves aligned over here. One is called as the air gap line, and the other one is a little saturating over when the field current is increasing over there. Now this process of open circuit test has been done that the field current is increased from maybe a zero value to some rated value over here, and then that field current, as it increases, the generator is totally unloaded. So what this means, that IA current is zero. This is very important over here. When you are increasing the field current, the generator is open circuited, you are not attaching anything on the output of your generator. So over here, the curve which you are getting over here, the dark line curve, can be called as EA or it can be called as VT, because they both are the same. IA current is zero over there. So this curve is completely having no armature current effect over there because IA is zero. Now the difference over here in this two dotted one and the dark one over here, as you can see over here, the air gap line is just a straight line, and we all know in air gap the mu naught, that is actually the permeability of free air space or vacuum, whatever we call it, that is equal to 4 pi into 10 raised to power minus 7 henries per meter. So that air gap line is actually that value. but a certain time comes, maybe you can call this point over here. At this point, when you increase the field current beyond this point, what happens? It does not follow the air gap line. Why? Because here at this point, what you are doing, the field current which you are providing to your DC rotor, or the rotor that is having a DC winding, that flux it is producing, it is flowing through the stator windings also, and it is saturating inside the core. Previously, before this point, in this region over here, the flux was very small. Okay? It was just linking a little bit with the stator windings, and that's why it was just producing a very small voltage up till this point. But afterwards, it saturates. This saturation is because of the material of the core. It can be the rotor core also, it can be the stator core also. The reason, because you know the reluctance changes as the core saturates, because any material what you are using over there, it is going to change its reluctance because of a different BH curve of that material. So this curve is plotted, that is the open circuit characteristics we call it, and we plot it with changing the field current from 0 to its rated value. We can call this one as IF rated over here, and this will change from certainly on the y-axis from 0 to the overall voltage that is actually going to be produced out of it, that is at no load. So this is the open circuit characteristics. Now if I move on towards the short circuit characteristics, as the name suggests over here, now this curve is very different from the previous one. Now what you are doing over here, now if I draw the equivalent circuit of my synchronous generator over here, let me just draw it over here. If I have a synchronous generator, we know this is the induced EMF inside that generator, this is that RA, this is that reactance that is actually incorporating the self-inductance and here I have done a short circuit. So this means that this is RA, this is JXS, and this is EA. Now you have done a short circuit. Now here you are not going to increase from 0 to the rated value. This is very important, because if you will increase it to the rated value, your current is going to be so much that the windings that are inside the machines, they are going to, so the current which is going to flow over here is going to be very small. So when you are going to have from 0 to IF, it will be a straight line. Now the reason of having a straight line is this over here, it will reach the maximum value of EA very fastly. So maybe this is the maximum value of IA at this point, so I can call it IA max. So this can reach with a straight line. Now interesting thing over here, that if you see this diagram over here, in hit over here there is V phase equal to 0. We have short circuited it. So the equation, if I rewrite the equation over here, what was that equation? That was EA equal to that was equal to V phase plus IA RA plus JIA XS. Now here this term, let me use another color over here. So this term has gone 0 because we have short circuited. So what is now the equation? This is EA equal to, just I can write it, IA RA plus JIA XS, even in the vector form. Now how this vector is going to be formulated, now this is very important over here. Now when you are going to write down the draw the vector over here, since there is no V phase, there is no V phase over here, so what I am going to do, I am just going to call it a dot. Now V phase is not there, and I since know that my current which is going to flow over here is lagging. Okay, so this is my IA over here, and if I have my IA RA, this is my IA RA, and then the next angle over here, let me use another dark color over here, 90 degrees to this one, this is my JIA axis. Now since we all know from the point of the starting, since V phase is not there, the only last vector that is required over here is going to be this one. So from this point to this point, this is going to be EA. This is going to be the phasor diagram for this equation when you have short circuited the synchronous generator over here. So this is the phasor diagram when V phase is equal to 0. Now the interesting thing over here is this, that you can find out your IA, or you can find out very simply mathematically over here. This will be equal to EA divided by RA plus JXS. Now this will be in the complex form or the polar form over here. So if I just want the magnitude of it, this will be equal to IA divided by EA over RA square plus XS square, and this will be the square root. So this is very important over here, that IA is equal to EA divided by RA square plus XS square. So what is happening over here, since RA plus XS square, they are very small value. So EA, that is still very small, because why? The field current which you are providing over here is very small. It's not going to go even towards the rated value, but you are going to reach the IA max. So this is going to be a straight line. The core is never saturated over here. It's unsaturated core over there, and in the open circuit it saturated a little over there after it was going to bypass the, or going to go away from the air gap line over here. So this is the phasor diagram over here and the equation. Now very interesting thing, before I proceed on how you are going to use these two open circuit and short circuit test for the values over here. Now if you see this phasor diagram over here, since they have done it in your book, over here I want to do this one in front of you. This is EA, this is IA, this is JIAXS, and this is IER. Now if you remember your phasor diagram we did in the equivalent circuit over there, what was IA producing? IA was producing BS. And what was VEA producing? EA was producing BR. So if I draw the magnetic phasor diagram of the same equation over here, the same one over here. So what I will be having, supposingly I have the first vector. Let me draw the first vector. EA is straight line, so this means that I have going to have this as BR. This is going to be BR. So just like EA, proportional to it, same direction, straight line, horizontal, this is BR. And then I have this one as, let me just draw another one. So this is IA. Since IA is going like this over here down, I'm not going to draw this one over here. So practically if this one is IA, I just drawn it dotted. So perpendicular to this one, this is going to be my BS. Now over here, if you add head to tail rule, so this is the BS added over here. So what happens now, that this vector, this is that parallelogram you want to actually, this is that B net. I hope this is clear over here. So BR just in phase with EA, BS, which is actually the stator magnetic field, which is 90 degrees to the overall. Please remember, IA is not in phase with B net. I've just not drawn it. I just drew it over there so that you can actually have this BS and BR, and then you can add these two vectors, you have B net. So BS and BR, they are combining to give you B net over there, and it's a very small quantity over there. Now, coming back to our open circuit and short circuit test, how you are going to use these two. Now, what is RA plus JXS? This is equal to, we can call it as ZS. That is actually the impedance of the generator. Now, since I am only interested in the magnitude, I am not interested in it, so I can call ZS magnitude equal to RA square plus, in fact, sorry, this will not be J over here this time, because this is XX square equal to. Now, this will be equal to, if you see this equation over here, this one, what it is equal to, the same thing on the denominator, so I can call this one as EA divided by IA. Now the question here arises, how you are going to find out EA, how you are going to find out IA. Now, if you see in this short circuit test, since you have short circuited everything, you have no idea what is EA. Yes, you have an idea of IA because you know at which point you are applying it. You can find out IA because you are just having an ammeter over here. You can easily do it. So that's an easy stuff. But how you are going to find out this EA over here? So EA is actually going to come from the open circuit test, and IA is going to come from the short circuit test at a field value current. I'm again repeating. Since Zs is equal to EA divided by IA, EA is not available in the short circuit test, so certainly this has to come from the open circuit test, and IA has to come from the short circuit test. So these two tests are going to give the two values in the numerator and the denominator respectively at a designated IF, at which IF you want to find out over here. Now over here, seems quite easy. The one value you are getting from the open circuit test, the other value you are going to get from the short circuit test, seems easy over here. But one approximation which the book is also done, since we know RA is very small. So what they have done, if we ignore this RA, its square will going to be a very small term. So what they have done, XS can be called as simply as EA divided by IA, and this again EA coming from the open circuit test and this coming from the short circuit test at a designated IF. Now that IF can be the rated value, can be some mid value, can be some very small value, can be some other value. But here the problem comes over here. The problem is not the approximation. That approximation may be just like a 1% error or maybe like 0.5% error, not more than that. The problem here arises because if you are taking this IF at the rated value, which is actually the maximum field current that you can provide in your rotor, so this EA, which is being provided from the open circuit test, and if I go back on that one, we had a problem over there that when it was going to reach at some rated value, it was saturating. The value of EA that you were getting at open circuit test was saturating, or maybe not fully saturated, something partially saturated, and the value of IA you are getting from the short circuit characteristics, it is unsaturated. So this is a little difficulty over here, that you have one value on the numerator which is actually saturating, and the denominator value, it is unsaturated over there. So what happens over here, the curve actually, okay, now over here what you can see over here, I have combined open circuit test, short circuit test, and both of them have been combined. So what is done over here, if I just zoom it over there, this is the open circuit test, this is the short circuit test, they both have been combined, air gap line is also there, and on the y-axis I have my VT in volts certainly, or EA, which is actually for the open circuit test, and then on the y-axis I have my IA, which is for certainly for the short circuit test, and on the x-axis I have my field current, certainly this is going to move from 0 to some rated value. And on another axis has been added, which is XS over there. Now as you can see over here, what is happening over here, since if the open circuit test remains in the linear region, this region is linear, this one, so when it is remaining in the linear region, the value of XS over here, as you can see, it is constant. Why? Because the open circuit test is giving almost unsaturated core, short circuit test is also unsaturated, so it's not changing that much. But afterwards the open circuit test actually starts to saturate, which is actually the core is saturating because of the higher field currents, and the core is, the two cores, the stator and the rotor, they are linked up. So what is happening over here, you have this flux increasing, but excess value is decreasing down. So what is happening over here, whereas the core is actually saturating, the value of excess is decreasing, and which is completely true, because if you see this expression over here, if IA is increasing, EA should increase with the same ratio. But what is happening in the open circuit test, EA is not increasing with the same proportion now, even IF is increasing. So what is happening? XS value is decreasing down, as you can see over here. So normally, whenever you are going to talk about the excess value being found out, you're always going to find out in the unsaturated region. But as far whenever a generator is working, it can be moving in the saturation region also. So when it is working in the saturation region, you will have to take its designated value, and excess value will be different over there. So every time whenever a numerical comes in front of you and they have given you the open circuit test and the short circuit test graphs or whatever data, so you will have to find out excess at the required field current. This is very important. Otherwise, if nothing has been shown or nothing has been asked over there, you can only use this value of excess, which is at this point over here. So open circuit test and short circuit test, they're very easily over there. You can easily find out your excess in the unsaturated core or the unsaturated region, but afterwards it's saturating. But one thing very important, a little bit from the power protection point of view, this XS over there, which is actually the synchronous reactance, is very important factor in actually the safety of the equipment, because whenever a generator is going to be supposedly short circuited, this XS is going to limit the value of the current flowing through the windings over there. So the excess unsaturated value is always very high, but the saturated value is always going to be small, and the larger it is better. But on the other hand, if it is larger, then you all know the phasor diagrams, they actually have a lot of voltage drop, they have a loss over there. So practically it's one way, or it's basically how you are actually going to adjust it, that excess goes in higher value or lower value. It's a trade-off. You have to decide on it, that you want the safety first or you want a better results of a generator. Certainly for safety, you can have many other relays or many other fuses or many other breakers or any other type of other grounding techniques over there, which we will discuss maybe when you go in towards your third or fourth year of the power specialization. So this synchronous generator, this same circuit diagram and all this open circuit and short circuit characteristics will be coming into play over here. Meanwhile, this is just the test over here, in which you can actually find out the open circuit and the short circuit. You can find out this excess over there, but if you don't want to use this approximate, you can use this formula over there. Since you know your RA, you have done it already from the DC test, so you can do it very easily. You can just plug it the value and you can find out excess. But this RA, even plugging it in, is not going to do any advantage over here. It's just going to be a 1% or maybe 0.5% error, not more than that over there. So this is just a synchronous generator. One thing over here, please kindly have a habit of reading through the book. This is very important. One topic or one definition which I am not reading it, please kindly go through it from the book. What is the short circuit ratio of a synchronous generator? What is the short circuit ratio of a synchronous generator? This is given on page number 212. Please kindly go through it. It's very important when you go in the industry or something. Every generator is given a short circuit ratio. Please kindly go through it. I'm not telling it over there, so you have guys a habit of actually going through the book as well. Okay, now coming on to the last topic of today's lecture, which is actually a synchronous generator operating alone. Now, before I go on forward and discuss a synchronous generator operating alone, synchronous generators, they always work in parallel. Whenever there is, supposedly, I hope so, every one of you has gone towards the main powerhouse of our UET, and you have seen over there that there's a big powerhouse over there, and at some good times when we had the CNG supplied or the compressed natural gas available, we had those gas generators over there, and they were putting out approximately 3.1 megawatts of power over there. So that was a huge power, and that was enough for, and there were 3 generators over there, I guess 1.2, 1.2, so I guess 1.25 megawatts, 2 generators, and then the remaining last one was just a 500 or 600 kilowatts generator over there. So the total output nowadays, since the gas is not available, so they don't give it for the universities or any other generation. So normally we have a diesel generator or such stuff over there. But otherwise, synchronous generators, whenever they work, they always work in parallel conditions. They never work alone. But supposingly you are somewhere in a desert, or maybe you are somewhere in some river stream, near a river stream, and then you have a turbine over there, and that turbine is working over there through the water, and you are getting some constant speed output from over there. So easily you can say that you have the mechanical power available over there. So a synchronous generator will be working alone. But if a synchronous generator is working alone, what will happen when it is going to be having a load change? So this is very important over here, that how that load change is actually going to be taken up by that synchronous generator. Because when there are going to be synchronous generators working in parallel, like the one in Pakistan, which we call as the grid over there, because there are like 10 generators in Mangla, then there are approximately 4 generators at Tarvela, then approximately I guess 4 or 5 at Capco, then there are like 3 or 4 generators at Hubco, and I'm just taking the name. So there are many parallel generators, and they all are working in parallel. So even if one generator is not producing enough, the other one is going to give it back, other one is not working, then the third one is going to give it, and so on. But if a generator is working alone and it's only going to give current or give power to only one load, and then you switch on more ACs or more fans or more lights over there, what happens then? That is actually the topic of concern over here now. So before we go on further, again the article is divided into 3 parts. The first thing is going to be resistive load. Now this is very important, because here in this article I am not going to assume that my RA is equal to 0. I am not going to assume it. So I am going to draw the phasor diagrams with RA not equal to 0. So I am going to include them. Your book is having those phasor diagrams which are included. At the end of this lecture, I will show you that those 3 phasor diagrams, how they will look without the IARA. So these ones over here which I am drawing over here are including IARA vector. So the first load, which is actually a resistive load. So what happens in a resistive load? We will just draw the phasor diagram again over here. And when we are having this phasor diagram, this is very important now. Now this diagram, you can't make it with according to some scale, but a little freehand something, so that the lengths are approximately the same. So this is my V phase over here, and since I am going to have my current, I'm just going to draw that current phasor over here. This is my IA, and then certainly this changing color is a little hectic one, but anyway, this is my IA. Now deliberately I am making IARA vector a little large, so I hope you don't mind it, so that you can actually see this thing. Otherwise practically IARA and J-axis vectors, they are very small. Now the perpendicular to this vector, this is my JIAXS vector, and certainly the last vector, which is from this point, this is my EA. Sorry about it. Let me just this is my EA vector, and this is my angle. Now this is a generator working. What happens? The load current changes, which means a resistive load were attached, maybe like 2-3 bulbs are working. What happens? You increase the number of bulbs. You go from 3 bulbs to like 5 bulbs or 6 bulbs. What happens then? Now this is an interesting scenario. What will happen then? The current actually increases in magnitude, and it goes from IA to IA dash. Please remember, the magnitude has changed, the angle is not going to change, it's still a resistive load. Now what will happen over there? This is very important stuff over here. Please kindly see this, very important. Now if you remember your power equation, what was the power equation? Power equation was equal to 3 V phase EA sine of delta divided by XS over here. Now what was the power equal to? It was equal to 3 numerical constant V phase EA sine of delta divided by XS. Now if you see this angle of delta, this and this expression is EA, or this length is actually equal to EA sine of delta. Now if V phase is not changing, this is very important one over there, if V phase is not changing, then certainly this means that this IA axis vector length, this purple color length, is going to increase. But here your V phase will change because the synchronous generator is working alone. So what will happen now? Now since we know IA is equal to K phi omega. What is K? Machine constant. What is flux phi? Field current, and it is constant. You are not changing it. Sorry. So this omega, it is also constant. Why? Because you aren't a constant frequency. So the speed is constant, the field current is constant. So the length of EA vector is not going to change. Then what will happen? How you are going to accommodate a larger length of IA dash, which has increased from IA. Now, one thing very important over here, if you can see this phasor diagram, this is EA, and if I have this one as EA, this EA can actually move in a circle over here like this. I hope you are getting my point, what I am going to try to say. EA, the magnitude of EA can only move in this circle, this dotted line I have drawn over here, but its magnitude will not change, its angle will change. So now what happens, if I'm going to use another color over here just for the audience. Now if this EA changes its orientation supposedly to this point, now what has happened, the length is not changed, this is now EA and still it's EA. The only thing that has changed is this, that this is delta bar. So now what happens, let me complete this phasor diagram. This is where now interesting. So now I'm going to complete this phasor diagram. Okay, sorry, what's this? This is my JIA bar axis. What has happened? The length of IA axis vector has increased. So what will happen here on the other side? That is actually the lower side over here. If I just see this one, what will happen? IARA vector is now going to be changed to somewhat this length. Now I am showing it with a dark line over here. So what happens? This is now IA bar RA, and the last and the least, very important, I'm using another color over here. This is now V phase bar. I'm again repeating this. This is very important. The generator was working at resistive load. The current was IA. What happened? You increase the number of bulbs so that now you have IA current increased to IA bar. Now the generator is working at a constant field and constant speed over there, which means constant excitation is there, which means that your flux phi is constant, your speed is constant because you are having a constant frequency requirement. So what happens? EA length is not going to change. The only way is this, that EA changes its angle with V phase. And if you see over here, when you are going to move this vector from this purple to this yellow color over here, this is the only way you can have a larger length of JIA dash axis. And in this way, then you have larger length of IA dash RA. Why larger length? Because IA magnitude has increased to IA bar. So what happens? Who pays the sacrifice for it? The sacrifice is paid by the phase voltage, or actually the voltage at your load. So what happens? You increase the load over there. What happens? The load voltage decreases down. Your phase voltage available from the generator decreases down when you are increasing the magnitude of your current, not the phasor angle or changing is there. Only the magnitude is changed from IA to IA bar. The angle. Now if you see this from the power angle point of view, what has changed? EA magnitude still the same. V phase, yes, certainly it has dropped, but sine of delta angle has increased. So the increase of sine of delta angle is more as compared to V phase. Now one thing very important, I have shown this V phase from V phase to V phase bar a little larger so that this phasor diagram is readable. Otherwise, in practical case, maybe the drop is not going to be more than like 1%, 2%, or maximum like 3 or 4% if the change was just 1 or 2%. But I have shown this deliberately over there. So the EA vector, this vector, which we can call it as proportional to the power, because this EA sign of delta bar is proportional to P, which is actually EA sign of delta bar. So what has happened? The power has also changed from this purple color over here to this blue color over here. So the length of this y-axis over here, that is EA to EA, the magnitude is still the same, only thing changed is the angle. So this is how the generator, which was working alone, changes when the load changes from one magnitude and it increases. And now you can show this one in the reverse direction as well. Supposingly the question is asked, how will the generator behave when the load is decreased? So you can take IA bar as IA, and then you can take IA as IA bar, just opposite or vice versa of it, and you can see the difference. What happens when the load decreases, the voltage will increase over there. But when the generators will be working in parallel, you will not be seeing this thing. Why? Because whenever the generator is not giving you that power, maybe another generator at some other station is going to control that power or going to give you that power. Okay, we will discuss this one. It's a little complex strategy over there, but a synchronous generator, when it is working alone and it's a resistive load, then you can have something like this waveform. This is including IARA over here. Now if you do not include IARA, let me show you how it happens. Okay, now you can see over here the phasor diagram which I drew over here was incorporating IARA, since I assumed that RA was not equal to 0, but in your book they have drawn it without the IARA vector, and it's fairly simple, but please kindly have the strength to actually draw that from IA to IA bar and including the IARA vector. So you can see again this is a semicircle, the value changes from EA to EA bar, the magnitude is still the same, the only thing that has changed is from delta to delta bar. So what has happened, the voltage changes from V phase to V phase bar, it has certainly decreased. So this means when the load increases in a resistive load magnitude wise, then what happens, the phase voltage decreases down, the load voltage also decreases. Now the next thing that is very important, or the 90% of loads which you encounter are inductive load. So when you have an inductive load, what you are going to actually do, now here again I will draw the phasor diagram first over here. Now I will draw it a little below. So this is my V phase, let me draw it over here. This is my V phase, and I have it this is my IA vector, and just parallel to this one, this is my, I'm just using the same color, not write it over here, sorry, this is my IARA vector. And if I use the other color over here for, let's use this orange one, so this is my 90 degrees JIA axis, and then the last vector which is actually EA, let me use another color, and this is something like this. So this is my EA, and certainly the angle over here is delta, this is angle theta. So this is the phasor diagram. We have done this already. Okay. Now what happens over here, again the load is increased. So what happens now, IA will change its magnitude from IA to IA. I'm just drawing it on it. So the magnitude is not changed. The magnitude is changed, the angle is not changed. So IA has changed to IA bar. Now again same thing, if I draw this as an x-axis over there, this distance over here is proportional to P. Now when the load has increased, there is only one way that you can have it move, is this, that let me use another strong color over here, and so you can only move this EA vector in the above direction or the below. This is the circumference over here of a circle over here, which I've drawn just as dotted over there. So the only way is this, that you are going to have an increased value of power, is this, that your EA changes to something, this value. So your EA has changed to supposedly EA. You can call it EA bar, but since the magnitude is the same, the only thing that has changed is this delta bar. Now when this has changed to, in fact this is a little, this is my delta bar. So now what is going to happen, when I'm now going to complete this diagram, so the diagram is going to be completed in such a way that this one is my length and this one is my IARA and this is my JIA-XS. This is my IA RA or IA bar RA, and certainly the last but very important vector is this one, and this is V phase bar. The same thing has happened. The two triangles which we are seeing over here, they are completely parallel to each other. This is very important, and here I have deliberately shown a larger decrease. Okay, but practically the decrease will be very small, so I deliberately increased this over here so that it is visible to you. What is happening over here, again, the magnitude of the power over here, this one was equal to P, this one is also, you can call this is proportional to P bar. And what is P bar? P bar is actually equal to 3 V phase bar EA sine of delta bar divided by XS. XS is constant. The only two things are V phase and sine of delta, which are changing. The other things are constant. Why they are constant? Because we are not changing the DC field excitation. We are not changing any other thing over there. So again, in an inductive load, the decrease is more. As you can see in the resistive load, the decrease was small. Okay, the decrease was small. But here in inductive load, you can see when the load increases and you are not doing any changes on the excitation. Now how you are going to complete it, like how you are going to remedify it? The only way you can remedify it is by increasing the excitation, because we know EA is equal to K phi omega. Omega cannot be changed. This is very critical. Frequency is very critical. If you change it, the speed of your motors which are working over there, the speed of your fans and all that stuff, it will change. The diodes inside your power supplies or maybe your rectifiers, they will have a very different prospect over there. So the only thing that you can change is actually this flux phi or IF over there. So when you want to make this up, you want to remedy it, only thing, change the DC field current flowing inside the magnet, the rotor over there. In this way you can bring back from V phase to from V phase bar. So this is the synchronous generator working alone under inductive load. Okay, I will show you the book waveform a little later. Let me just complete the capacitive view. The capacitive load, which is very important over here, and the capacitive one over here. This is the capacitive load over here. Now when you have a capacitive load, now this is very interesting diagram. Why interesting? Because here this is my V phase and I have now a leading current. So when I have a leading current, this is my IA, okay, and I have to now include IARA. I hope these are two parallels. Please practice these ones very importantly, because these can be asked definitely in the exam. So this is IARA, and then I have the IA-XS. This is my JIA-XS, and the last but the least very much important one, which is this is my EA, and certainly this angle is delta. Now what will happen when the magnitude of the leading current, which is the capacitive current flowing over here, it increases from IA to IA bar. I'm just showing it a little away from IA, so both vectors are visible. Otherwise you can draw it on it and then you can just show it, it's going over there. Now what has happened, the capacitive load has increased. So now again the condition is the very same, that your current the DC rotor winding, they are the same, it's not changing over there. So what is going to happen, that is going to only move in the circumference over there. Now when it is going to move in the circumference over there, let me actually draw this one. This is, okay, sorry. Okay, let me draw the circumference. This is still it's not the very best anyway. So this is IA bar, and when it is going to change, this is going to go like this. So now what is going to happen over here, still not the very best of the line. Actually you don't have a length over here. Anyway, sorry, this is my arc, a little bit arc over there. Now the only way you can accommodate a larger length of JIA axis is this. In fact, let me just remove this and have a different color. And sorry about this. And this is my JIA axis. And certainly, let me just remove this. Let me just draw another one. This is a little difficult diagram. The reason behind it is very, very simple, that over here like this. Now this is IA axis. Now the only way you can have a larger length of JIA axis, or actually IA dash axis, is this, that you are going to increase the length of EA, the angle of EA, in such a way that you increase it up till this point. So now the angle has changed from delta to delta bar. The value or magnitude is still the same, and now this time you have, let me draw with another, like this. So this is my JIA bar axis, and then with the other color over here, this is my IA bar RA. And the last but very, very important one over here, what has happened, I'm drawing it over here. This one is V phase bar. Now again, let's see this one. This is very, very important. What has happened over here, please, these are not straight lines because I'm doing it a very freehand sketch over there. Please draw them. These are very, very important curves over here. So I hope you can repeat it over here. Now what has happened over here, the length of IA axis has to be increased. So the only way that EA improves from this angle to delta, from delta to delta bar, and this JIA dash axis length is increased, and certainly IA bar RA length is also increased. So the only way is this, that this one, okay, sorry, the only way is this, that the phase voltage, that is V phase, increases its length from B bar to, from V phase to V phase bar over there. So what is happening, an increase in load, in capacitive load case, what happens, the V phase voltage, it increases. And why it increases? Because the capacitive current is there. it's already providing you the reactive power. And this is the same thing that happened inside your transformer over there. So the same thing is happening over here for the synchronous generator over here. And in the inductive load case, as you can see over here, what happened over here, that the load increased in magnitude, which means that IA bar or magnitude increased over there. So what happened, the V phase magnitude, or actually the length, actually decreased down. And the same was true for the resistive load, as you have seen over here. So these are the three phasor diagrams over here. This one is not very good, but anyway, still it's legitimate over here. I hope you can practice this one with different colors. This is very, very important in the exam as well, that you draw it with different colors, because otherwise the teacher cannot understand that which one was drawn first and which one was not drawn, and it's very difficult to actually understand. So kindly, whenever drawing these phasor diagrams in assignments or in exams, please draw it with 2 or 3 different colors, just like over here, so you can actually show that what has happened. This angle has to be 90, this angle has to be 90, at least when you are drawing it with a free sketch, because they are not according to some scale. This is very, very important over here. So again, you can see over here, if I draw the perpendiculars over here, this one is the proportional to P, and over here this one is proportional to P bar. So you can see over here that the EA sine of delta, which we call as P equal to 3V phase EA sine of delta divided by XS. So what has happened, this delta has changed to delta bar, V phase has changed to V phase bar, and what happens, actually this P changed to P bar. So this is the case. So in capacitive load, you have the load voltage or the phase voltage increased over there when you have increase in the magnitude of the capacitive load. Okay, as I just told you that in your books they have not drawn them according to, or they have not drawn the IARA vector. So the inductive load diagram, as you can see over there, it becomes relatively easy, because if you see the inductive load diagram, to accommodate this triangle and then increase the value. One thing very important, just a small hint, whenever you are drawing this EA circumference or the circle over here, please use some protractor or whatever, or some compass over there, so that you can actually have a legitimate circle over there. Otherwise, if you are going to draw it with freehand, it's not going to be the accurate one. So this is very, very important. As you can see over here, the circumference of the circle is drawn, and you can see the magnitude changes from V phase to V phase bar. The answer is very same. And if it's the capacitive load, as you can see over here, what happens, the phase voltage changes from V phase to V phase bar, and actually once it increases over there. Why it has increased? Because the magnitude of the current has increased. Magnitude has changed. The angle of the current still is theta, it's not changed over there, and this one is proportional to your power P dash, and this one is proportional to your power P. So you can see the Y component of the EA vector is increasing. So this means the load on the generator is also increasing, but since this was a capacitive load, so what is happening, the phase voltage is increasing. Now in this case, if we want to remedy it, and you have a capacitive load which by chance is not going to be there unless and until you have deliberately some capacitors attached over there, because capacitive loads are normally not found in load centers or anywhere else. But still, anyway, if you have to remedy it, the only way possible is that you will decrease down the field excitation, that is the rotor DC current which is flowing over there, that is IF over here, so that in this way you are going to decrease down your V phase. Because one thing very important for loads, if you are going to run maybe like a 220 volt fan or 230 volt fan at 200, maybe it will work a little slow, because the current is going to be small, flux is going to be small. But if you give a 230 volt fan or something 250 or 260, you are going to burn down the insulation. So this is very, very important that your voltage is under control, and that's why a synchronous generator working alone is never the solution. Whenever we are going to have a synchronous generator working, we are always going to have them in parallel with some other generators, or The other word used for it is actually grid, which we will talk about in the next lecture. Very important one, because in this way the paralleling of generators on the grid is actually done, and that's a very difficult process over there, and this process takes some due time over there. I hope today's lecture was enough. This is covering article 4.6, 4.7 and 4.8, and I hope please cover these two, and very importantly the examples over here at the end of this articles. Example number 4.2, 4.3 and 4.4. These are solved examples in the chapter. Please kindly go through these 2-3 examples. These are very important ones from the exam point of view, and I hope they are easy for you, because they are employing the phasor diagram. Then you have to apply some trigonometric or Pythagoras theorems over there, so that you can actually find out the lengths of the vectors or whatever the phasors over here. Next time we will try to cover 4.9 article and 4.10, so that we can actually move on towards the end of this chapter. So I hope this was nice for you. Thank you.